So let's start with the policy gradients. And uh, we will be reading from policy gradients up to maybe Q learning. Maybe we should cover because Q learning then or Q learning and exploration policies and approximate Q learning and deep Q learning can be clubbed together too. Uh, so let's do Q learning. Uh, we will cover till Q learning and we will look at the code too. So
Oh, and what time should we reconvene?
yeah. Learning.
7:30?
Well, yeah, 15 minutes will be
15
enough.
or 50 minutes? Oh, okay.
50.
So 7:30 is 48 minutes. Is that good?
Yeah,
Okay.
cool. I will just set up a timer. Uh, let me- Hey guys, how it's going? Mm, Hi, could you guys hear me?
Yeah.
Hmm. So, did you guys read through Q-learning, or if not, we can yeah, take this in the next session too. There's no hurry, but we need to understand every aspect of this.
Yeah, I didn't quite get through it. I didn't quite get through Q learning.
Okay, cool. So let's begin through policy gradients and see uh, the time permits us. Mm, Firstly, the reinforced part. So last time we covered till evaluating actions, the credit assignment problems. And if we take a look at the notebooks, let me take, uh, let me share my screen first. Could you guys see my screen? My pie chart and this window, Chrome window.
Yeah.
So we covered this last time with respect to the simple hard-coded policies in which we had rewards of the this is a basic vanilla case of solving the uh, hard-code problem. Uh, this is the simple hard-coded policy that we coded, and then we took a look of visualizing it and the animation of how it performs and how much time does it take. It was unstable. Then we had progress to the uh, mm, dense layers and with respect to uh, stacking of multiple layers for the neural networks. And here we had two layers. First was the ELU activation with a dense of 5 units, and second was one with a 6 sigmoid. And uh, then we had the parameters that we needed to consider. Mm, then, uh, since we did not have noise, then we took an action based on that particular uh, how do I say it? That simple one step that that meant uh, uh, it contains the environment's full state, so we didn't have to take our sequence of past actions into consideration here. Then we progressed on to the policy network, in which we had the right balance, the difference between the exploration and exploitation for the actions that were well known. Uh, how do the agent tries to differ between them? And then we had this, in which we formulated our rendered policy net, uh, uh, a model which this action, uh, this step range, and the action that it took, and the prediction with respect to this formulation of the uh, two-layered deep neural network. So it's a nonlinear since ELU activation has been applied. Nonlinear deep neural networks. Then we took a view at the render policy, and it didn't perform as well as it should have, but it was better. And then we had this was with respect to the uh, custom applications of the gradients here, uh, uh, the trainable variables, and backpropagating those gradients to those two networks. So here they have only taken one environment, that's the cart pole V1. And from the implementation perspective, they have used a simple RMS prop optimizer and a binary cross entropy loss. Since you have two outputs as to move left or right to balance the cart. This was the code of how those iterations are performed in with respect to TensorFlow. If we code it from scratch, from the with the gym environment, and mm, this is the if we go through it, this is the target probabilities, which selects the one or a zero gradient tape, left probabilities, then the reduction of the mean from a loss function that we selected. Here we select this guy here as a loss function. Where is it? Where is it? Yeah. Here are losses binary cross entropy. And this ras and apply gradients that are passed, and then the actions which are selected based on that. So here, I think, yeah, the actions, random environment, the greater, the left from certain numpy, okay, and then as type, this converted to int32. This will return a Boolean value. Then what they are doing here is uh, the step actions with respect to those environment index, and then the observations. If not done, if we have not reached the final state or the stability condition, then else the environment is reset, and we have the other episode that we need to. So this it goes through the number of iterations. In the end, there's a loop that closes that environment. This is the policy animation, then it's being called, and this does not wobble as much because, yeah, due to the number of iterations that have been done. I think so, yeah, there has been 5,000 iterations, and the number of environments that it parallelly ran on was 50. So, hmm, let me. This was the summary of the last time, the things that we looked at with respect to the evaluating actions and the neural network policies here. Now let's get to the next, the policy gradients part of it, in which we apply a combination of which apply uh, how do I say it? Uh, Algorithm that's derivative of reinforce. Reinforce the kind of a algorithm that is a popular class in reinforcement learning, and many of the uh, uh, techniques and implementations are derived from it. So then we go on to the neural network policy. Then we get to view the 4 steps that are required for the policy gradients to uh, mm, to implement this. Uh, uh, as above, they have iterated this. This is, I think so, uh, sequential application of those iterations, those in environments that we are in, uh, if I'm not mistaken. Yeah, because I do not see anything that's being implemented here parallelly. Yeah, I was a bit mistaken here. Yeah, then and let's go down to the policy gradient. What they are trying to do is firstly calculate, compute the gradients. Well, let's look at the code, and then we will get to the gradients and how the gradient descent step works in the end. So uh, 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 here it gives an overview which is concise and apt. It firstly it plays the games multiple times in the or multiple episodes are taken into consideration. Then it takes the action of the good episodes that are slightly more likely, while the actions in the bad episodes are slightly less likely, and it uh, assigns those positive or negative gradients to the good episodes, and negative gradients, kind of negative gradient to those slightly less likely episodes. And then we play and we uh, kind of uh, go back to the in retrospect to the passing those, how do I say it? If we think of it from a deep learning perspective, we compute those gradients and backpropagate it through the layers, and then we sample those probabilities according to those uh, trained networks. So the first is the play step here. Play one step. Here we have the tf.gradient tape. Firstly, we have the environment, observation, model, and loss function that we had. The left probability here is this guy, and we are reshaping it as a np.new axis since the model takes a single vector into account. And then we have those actions, which is taken from a uniform, and this gives a Boolean value if it is greater than the left probability. Your left probability is this, which is taken from. It's a kind of a simple instantiation. Or you can say a bootstrapping, uh, which is done here. Uh, Let's play one step. Look at the details of how this value performs. We will take a look at it later in the code. Let's not worry about it here. Then the Y target. The Y target is your constant That's one. And then this action, that Boolean value is being cast into a float 32. So it will give a 0 if it's moving left, or 1 if it's going right. And then the loss function is there, which is the reduce mean. I think so. They have again applied a binary cross entropy loss. Yeah, because there are only two action value pairs between the y target and the left probabilities, the inputs and the predicted uh, A inputs and the outputs, and then those grads, which we taped here, uh, passed on with respect to those loss and the training variables. Uh, yep, and then this step is applied, and for one step, these four parameters are passed back. So this defines the one step function. I hope this is clear. Uh, uh, Please interrupt me if I'm moving too fast or something is unclear. And then we create another function. And so this is all the text that I just described here. Uh, then gradient loss with respect to model variable, depending on how would the action is uh, to be. Uh, then we apply those uh, new observations, the reward, whether the episode is ended or not, and of course the radius that we just computed. So this is with respect to the first step. Then we go on to the play multiple episodes. Here, this uh, this is a small X. Uh, yeah, that's the same thing that we discussed earlier. This text on the left, and the play multiple episodes. We take two lists, all rewards and all grads, and then we iterate through the episodes with current episode and the current grads in mind. These are the internal lists, and after each environment is reset, we play on one step. That's the same function that we used earlier. And we pass on those four environment observation model and the loss function that we had. And we append this to this guy here, the current rewards, current grads. If done, we break out of this loop. In For the all rewards and all grads, we also append this. Uh, in the end, for the multiple episodes, we return the rewards and the grads. So this is implementation of the multiple episodes. Let's take a look at the text for today. To, yeah, they have given hmm, function play multiple episodes in which they have executed this 10 times, and we took we what the next step is to go back, look at all the rewards, discount and normalize them according to those likely attributes that we had. So basically what it does, what uh, policy gradient here does is the third point here from the top is the meat of the policy gradient approach. So if the action's advantage is positive, it means that the action was probability good, and you want to apply those gradients computed earlier to make the actions even more likely to be chosen in the future. However, if the action's advantage is negative, and it means that the action was probably bad, and you want to apply the opposite gradients to make this action slightly less likely in the future.
Mike, I have a question.
Yeah.
Let's see. So let's see. On step 4, on step 4 on that page, it says finally compute the mean of all the resulting gradient vectors, blah blah blah. I think what it means is compute the mean of all the resulting scaled gradient vectors. That is, gradient vectors scaled by the advantage, scaled by the action advantage. I think that's what it means there.
Yep, in the code, if we look at it, that's the mean. This is the reward mean and the standard deviation. And for how they have computed the mean of the resulting gradient vectors is using this step here. So for all the discounted rewards, uh, they have calculated the specific discounted rewards minus the mean of that particular uh, uh, episode. Yeah, the flat rewards, and they have divided it by the rewards of the standard deviation. So it's kind of a normalizing unit that is being applied to reduce the variance here.
But what happened to the action, to the idea that they were multiplying the gradient by the action advantage in order to account for how much, how much that should be weighted?
That weighted is with respect to those, yes, discounted steps here,
Yeah. So in
in
three,
which
in number 3, in the item 3 there, it says the solution. The last sentence in item 3, it said the solution is simply to multiply each gradient vector by the corresponding action advantage, by the corresponding actions advantage. So I'm expecting that they're not going to want the mean of the gradient vectors. They're going to want the mean of the scaled gradient, that is the gradient vectors multiplied by the advantage.
yes, yes. If you formulate this mathematically and we expand it, then at each step, yeah, I think so. I'm not
Okay,
wrong,
that's
then
just something that occurred to
yeah.
me that I don't quite understand. And then I have another question. If you could explain what is the discount? I mean, they talk about discounting and multiplying things by a discount factor gamma, but what's the rationale for even having a discount factor? Why should gamma be anything other than 1?
Gamma should be anything other than 1 to get a view of uh, what the discount factor will be in the future episodes, because how much we want to take a weight of each action that of each reward that has occurred in a particular time step. So the in the end, those return will be a summation of. I think so. There is an example.
So I understand how it works mathematically, having a gamma of 0.8 or whatever. But why is there a gamma? Why is there a discount factor? What's the point of having a discount factor?
Yeah, if you take a look at an example, I think so. Yeah, here it is. Yeah, say there were three actions, and after each action there was a reward. First 10, then 0, then minus 50. And if we use a discount factor of 80%, then the third action will give a minus 50. That is the full credit for the last reward. But the second action will only get minus 40. That is the 80% credit for the last reward. Because it depends upon the squared. Uh, uh, if, if we write it down, the gamma increases which with each step, or howsoever we formulate our problem. Then for the first action, it will only be get we will only get a 80% of minus 40. So So that's the sum of that, and minus 32 plus the full credit of the first reward, that is 10, which leads to a discounted reward of minus 22. So this is an example of how those discounted rate works with respect to applying it mathematically.
Mhm.
And what it does is uh, uh, if our uh, action in the end was a suppose we are computing we are working on a hill task in which your agent needs to stay on a hill,
Mhm.
and if it falls, so you will get a reward of minus 40, minus 50 here. So
Mhm.
that's what it's trying to how do I say it? Pass it down back to the uh, original mm, uh, return that we have. So if
Joseph, at least conceptually, I try to think of it as a knob that helps you um, tweak kind of the analogy I draw is to the time value of money, except with a knob that doesn't always make it worse in the future, but can increase or decrease. And the knob is gamma.
So is it a penalty for taking the right action too late or something like that? Is that?
So it's more, as he says, that it is discounting future rewards versus current rewards. And how much you want to discount is how you determine, or is so he has the paragraph in the text which says to tackle this problem, and it starts with to tackle this problem, and there he gives the example of if the discount factor is close to zero, then future rewards won't count for much compared to immediate rewards. So that's like the time value of money where you discount
Okay.
future,
Okay.
compared to
So
inflation.
is this a way the knob is something about greediness? Like if the if gamma is zero, then we're looking only for immediate reward. If gamma is other than zero, now we're trying to balance between immediate reward and future reward.
That's right.
So we're going to a non-greedy situation.
Yeah. So yeah, I wouldn't. Well, I don't know about greedy because greedy has other implications in CS, but yes, analogous to that, which is immediate rewards versus future rewards and the balance between them. Because he gives the example of if the discount factor is 0.95, then 13 steps into the future, the rewards count for half as much as immediate rewards because 0.95 to the power of 13 is 0.5.
Right.
And with 99.99 discount factor, then 69 steps into the future, the rewards count half as much as immediate.
Right. So it has to do, the knob has to do with how much you're focused on, how
Short
much you
term,
want to wait to the future rewards.
correct, versus the immediate rewards.
Yeah, that's really helpful. Thank you, Srinivas.
in the future, if when we take a look at the Markov decision processes, there is a tweaked discount factor in which you have to pass through fire to get the maximum return possible in your uh, uh, final how do I say it? That final return and your uh, policies that could compute the optimum uh, not the optimum but the greedy with uh, not greedy too but let's take a look at afterwards. Mixing too many words here. uh, yeah. So this was it with respect to the discount formulations and how they affect uh, action, the normalized reports. Mm, I think so. We have covered play multiple episodes here.
Sorry, Mike, Joseph asked the second question, which is where in the code is that um, multiplication thing that he refers to done?
Mm,
The gradients, blah, 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 multiplied by the something actions that he talks about.
yeah, so the flat rewards. Then after this application of this guy, yeah, all rewards and the discounted rates. And this is the we enumerate it, and then we append this mean gradients here, and then we apply this uh, as a zip of mean gradients and the trainable variables, and we pass it down the uh,
So that line where he's zipping it and then applying the gradients is when the mean gets multiplied to the training gradients.
yeah,
That's
yeah,
that line is doing, Joseph, what you pointed to.
yeah.
Which line is that?
That's the zip
Uh,
and the gradients apply that has a that Mayank has highlighted.
Let's see. I see a red dot up on
Right.
top
Right.
by model of obs.new np.new axis. Is that?
No. If you are looking at Mayank's screen where he has a red dot and
I see it on the left side.
Yes.
I see it.
So that line is what is doing what you asked. The second question you asked of where is the multiplication done with the gradients?
All
Because
mean
it's
grads.
zipping it and then applying the gradients, right? So it apply gradients, I would assume, multiplies the mean with the trainable variables.
Yeah, but what happened to the what would you call the thing? The action, the action or something like what was it called? Advantage. It was somewhere it was saying that we were going to multiply the gradients by the advantage and weight them by the advantage. So where is that getting done?
since these are the if we take a look at this line, let's break this line up.
Fine.
Pf dot reduce mean. This line. Okay. Let's break this line. Let
Oh,
me
there
get
it
to
is. I
this.
think it's final rewards, right? It's final rewards is the advantage, I think.
Mhm.
And there it is being multiplied by the gradients.
Yeah.
Mean grads, yeah, it's getting, the gradients are being weighted by the final reward, which is being multiplied element by element into the gradients. So that's where that gets done. Yeah, okay, that makes sense.
Mm, um, We'll take a look at this. Let me. Yeah. Yeah. So step and the final reward, we enumerate this. Then the sort index and the final rewards in this. Final rewards multiplied by all graphs. Next step variable. Okay. Yeah. Here it is. That's where it's being done. The mean grads. And then we have been applying that, and then we take those mean grads after through each iteration, and then we zip all those grads uh, with those trainable variables, and then we apply that.
Yeah, so I think the first part is
Mhm.
the final reward, and the final application of is
Mhm.
the optimizer apply. So that's where
Yeah.
actual gradients get calculated and applied.
Mhm.
Not
So
calculated.
this is, yeah. So this is on per episode, and this is for all the episodes. That's the return. of, you can say, the episodic tasks. So this is the inner loop here. And this is the outer loop, which gives the iteration of all played with
So
multiple episodes.
is it for, because the optimizer is in the outer loop, for it is for the entire iteration, correct? Or is it for the episode? Is
For
the
uh,
optimizer dot apply gradients, is it for the episode or for iteration?
this is for the whole, all the rewards and all the gradients that have been formulated, those 50 environments and those 5,000 steps. So if we take a look at that, that is for all those 50 multiplied by those 5,000. If we have multiple uh, uh, how do I say it? Those multiple environments that are being played in. We if we take that into account too, but here I think so. This is with respect to the multiple episodes in a single environment, since it makes a single environment here. So if sequentially we take a look at it, and it's having 50 episodes, and then so this will be a accumulation of those 50 episodes, the rewards and all the grads that are taken from that 50 episodes, and we are applying this here, and within each episode, those we reduce the final reward based on that episode index, the step uh, it took at each time step. Suppose if we take the cardboard problem, so if it is taking suppose going this way, and we are trying to move it right, so this is one or two steps that have been taken into account. Then so until that's stable, that's the one uh, episode, and we are um, giving a final reward to it, and then we are appending all of that in the end as a return here.
So that's per
This is,
iteration.
yeah, that's the return or the iteration. So let's move forward. Yes. Yeah, so, then we go on to this paragraph here for the discount rewards, return exactly what we expected. Discount and normalize rewards, normalize action advantage in both episodes. Uh, this gives a simple calculation as to the discount factor with respect to these uh, first and the second uh, series of steps that have been taken into consideration, the discount and the normalized reports. So we get the arrays here. It's just to assert your code into or test out your uh, discount and normalized rewards function. And then if we try to run these are the parameters on which we run the 150 training iterations, playing 10 episodes per iteration. And with episodes will last for mostly 200 steps with a discount factor of 0.95. So these are the hyperparameters that we take. The Adam, we use Adam with a 0.01 combined with cross entropy loss. So these are the loops that we just discussed. Yeah, this guy. This is the final report. Compute the weighted mean and the gradient for a variable over all the episodes that and all the steps that is weighted by the final reward. Then we apply these mean gradients using the optimizer here. This and tweak the policy a bit better. Then we can try out the policy gradients. So this is the default mean reward, and this problem is considered solved when the mean reward per episode will get close to 200, which is the maximum default in this cardboard V1 environment. So that's the done variable that we have. If it gets close to 200, I haven't looked at the exact value, but yeah, this seems like it. And then, this is with respect to injection of the prior knowledge into the agent, as with Bayesian methods, some type of priors with respect to Gaussians or some other kernels that can be inserted. Uh, this will make the pole as vertical as possible. This is a very simple A environment, but yeah, in complex cases we take a look at much more. We can have much more. How do I say it? Uh, in tough in environments that are easier, that we find it easier to apply those uh, methods to, and that will be beneficial in those cases. And reasonable good policy, example hard coded. This hard coded policy refers to the causal policy, those causal conditional statements that we can apply to imitate before it uses a policy gradient to improve it at those training steps. That's one research direction that many folks are taking to make their agents train faster. Here we have the simple policy gradient algorithms, which solve the cardboard task, but does not scale well to the complex task. It's highly sample inefficient, meaning it needs to explore the game for a very long time before it can make significant progress. This is due to the fact that it must run multiple episodes to estimate the advantage of each action, as we have seen. However, this is the foundation for a more powerful algorithm such as actor critic, which we will discuss. I will give some time to it too. And then there's another popular uh, class of algorithm, the family of algorithms to optimize the policies so as to increase the rewards, which uh, can be the agent learns to estimate the expected return for each state or for each action in each state, and it use the knowledge to decide how to act. And then this is a form of on policy versus off policy uh, algorithms, and we will see then via this MDPs, which are formulated here. So this now if take a look at Markov chains. So Markov chains are very simple, and they are simply a stochastic process with no memory. And it uh, it is simply a state action pair. And it can be formulated in multiple ways. Uh, there are multiple books on Markov decision processes, and how they can be applied to various problems with respect to those chains in practice. In I, I don't know, in continuous time domains and thermodynamics and uh, everything, in biological applications, uh, chemistry, that AlphaFold 2, if you remember that protein synthesis, it can be weak and applied everywhere. And this forms the basis of many of the, how do I say it, the cutting edge uh, uh, ways to the cutting edge research which is happening nowadays in reinforcement learning and in other avenues as well, which are using Markov chains to which are using some sort of a derivation of the Markov chains to solve those problems. Maybe next year we will see a rover on Mars, which uh, we can operate on. And they might already be using some sort of implementation of this Markov chains, but yeah, so it's there. And this is a simple S0, S1, S2, and S3 process that has defined those probabilities with respect to those transitions. Uh, uh, so if we start from S0, staying in S0 will have a 70% chance, and moving to S1 will have a 20%, and moving to S3 from S0 will have a 10% chance. And since if it reaches S3, it will remain here forever because of the 100% probability of. So this will be a final state, or this can be a end state. That's what they have described in this paragraph. And this is the Markov decision processes. And next we will discuss upon the Bellman's equation, which use Markov chains to have those those calculation of their optimum value and uh, uh, optimum state value functions, and the value iterations too. So how is that being done, or how is that being formulated in these settings? So here we take a look at the example of MDP, in which we have a state and the actions and those raw probabilities. So here the mm, uh, square here, A1 represents the action that it takes and the probability that uh, it has. So S naught A1 1, S naught A naught 0.7 to give back to S naught, then A2 zero point 0.2 S1. This is the kind of transitions that happen here. These are the possible discrete actions. So A1, A2, and A naught are the three possible discrete actions that are done at each step. Mm, then what they are getting to is that it's the probability of how those reward functions are being. If we take look at S naught. So if we take a look at the code too, we can on the left we can take a look at those transition probabilities. These are the three transition probabilities. Here only one is there. Here only one is there from A2 to S2. So here, this is the way this is formulated from S naught to A1. So S naught to S naught, from S naught to S1, from S naught to S2, and S naught to S3. That's a 0.7, 0.2, 0.0, and 0.1. Depending upon the action that has to be taken. I think there is a bit of a mistake here with respect to those here. From S0 to S0, it should be 1. Shouldn't be in the point where it is 0.2. It should be 1 here. Or I don't know. I'll have to take a look at this with respect to this transition from probability and how they are formulating it. Mm. Then if we move forward, then they have given a reward of how much 0.7 the 70% has a reward of 10 and the remaining state. So this is all a kind of a formulation, how they have defined this environment and the transition probabilities with respect to those actions. So that this is all the environment dynamics that has been defined here.
Yeah, I don't see the, in the cell that you were looking at to the left, line
Mhm.
2693, or line 694, there is no S3. So what is this, what does this mean?
I think so. They have taken different. This just this
it a
does not
different model?
accurately reflect, yeah, this particular example for Markov decision process.
Because I thought that was supposed to represent, figure 18.8, but it's obviously not representing figure 18.8.
Yeah, that's what I think too.
Yeah, yeah. Or
Or does it?
Oh, there it is. Maybe
represent
that's what
this?
it is.
Yeah.
That's the one.
Ah,
It's 18.7. Okay. Now let's
it's
see.
representing. Yeah.
Point
Yeah.
seven, point two. Yeah, that makes sense now.
Yeah.
Well,
that,
wouldn't it also be it's going S naught to
Mhm.
S naught, S1, S2, S3. So
Mhm.
probably it's what you're left with, 0.7, 0.2, 0.0, and 0.1 being the remainder.
Yeah, because 0.7 goes from S0 to S0 in the first line. The probability of going from S0 to S0 is 0.7. Probability S0 to S1 is 0.2 in the diagram. S0 to S3 is 0.1. That's the end, yeah. And S0 to S2 is not. There's no probability of going from S0 to S2 in one jump. So that's why that's 0. So at least the first row makes sense. And I guess we could work out the rest of the rows as well.
Mhm.
S1 to itself is 0. S1 to S2 is 0.9.
Yep.
Sorry,
S1 to S2 is 0.9, and S1 to S3 is 0.1. And then if we take a S2 only from S2 to S1, it's 1. Yep. So this makes
yeah,
sense.
yeah,
Yeah.
and S1 can't go to S0, so
Mhm.
that's 0.
Yeah. Yeah. That's
S1,
0. Yeah.
yeah. Okay, so that makes sense. Those numbers
Uh,
make sense.
yeah. Those make sense. And then this with respect to those. This is the diagram for 18.8
Yeah.
transition from probabilities and those rewards. That's what we were a bit confused. That's a state, action, and a next state. Yeah, the 0.7, 0.3, and 0.0. This, these three guys. Uh, for the particular A naught action, then yeah, for the A1 action, with respect to those transition probabilities for, sorry, the state S naught, then state S1, and state S2. I think so. These are the three rows, and those internal, since those. And those 0.7 has been mapped to this plus 10. This from, if we take a look at the figure, that A naught 0.7 has been mapped to plus 10 here. Uh, this minus 50 with respect to this guy from A1, when we, no, I suppose, yeah, from A2, if we are moving from S1 to, from S1, if we are moving to S2 via the action A2, then there's a minus 50 reward. Yeah, so that this is represented here.
So each sub item in transition probability is actually actions, right? For example, the first list within the list is action A0. The first
Yep.
index of transition probability is the state. But the next gives you the set of potential state transition probabilities of action 0, A0, right? That's the way to look at it. It's each of those three rows are states, and each of the values within the states are the probabilities of action 0. Then the next list is for action 1, and the third entry is for action 2 with the individual entries within it being transition probabilities to S0, S1, and S2.
Yeah.
Right, because point 3 is A0 action probability transition from S0 to S1. Therefore, it shows up in state 0, the first index, and then within that list, which is A0, it's to state 1 because it's at the second index.
Yeah. That's. I've formulated this before, but not using these two-dimensional. I use a simple dictionary term there. Yeah, this is a great way to do this too.
Yeah, but this one, you know, the states are implicit, the actions are implicit, so you have to be. But you know, you may want to make it explicit if you have multiple states and actions and stuff. So that's where a dict might be more easy to interpret than implicit interpretations.
Yeah.
Yeah, I think when you look at this, it's the rows correspond to the states 0, 1, and 2, and the columns correspond to the actions A0, A1, and A2. I think that's how
Right.
it works.
Yes, you're right. And within the actions, again, the probabilities are the actions probability to S0, S1, and S2 again.
Yes.
Because, right, the points, you can use the 0.7, 0.3, and 0. And that's why there is none, for example, because in the second entry, which is for state 1, there's no A2. Sorry, there is no A1.
Yes.
So that's why there's a none.
Yeah. Yeah, it took me a lot of time to figure that out, and I think it would have been better if he had explained it. But,
Yeah, that's why what Mang said of, you know, if it had been a dict, then you would, but then it would have to be dict of dicts too, right? So.
So this is, I think, what they have explained it. This is a simple formulation with respect to this diagram, which graphical representation on this diagram, and it asks us it by simply looking at this MDP. It asks a simple question as to what the strategy will be to gain the maximum reward over time. This is the path that he chose. That whether that agent should go through fire or should choose a different path. That's whole uh, kind of a greedy approach in choosing the best. If you start from S0 and uh, then the best option is A0, then A2, then uh, if we go on to A1 action, then yeah, we will be stuck in S0. But if we move to from here to this using point 3, using S1, it will have then no choice but to go through the fire to reach the S2 state. That has to take action A through. Or should it stay put here on the S1 state and should never reach S2? So that's a kind of a dilemma. And it's a good example too in trying to uh, take our earlier example into mind, as in if a Mars rover has to go through a ditch and to reach the other point. So what should it do? Should it go down to the bridge and go back up, or yeah, it should stay put and wait for some sort of help. So that getting out of the way, we will now take a look at a Bellman's equation quickly because we are over time. So Bellman's equations. Bellman used a way to optimize the state value of the state, that's denoted by V star, to sum the discounted future rewards the agent can expect on average after it reaches a state S and assumes it acts optimally. So here the optimal equations. Uh, this is an optimal state value, and there is an optimal this guy here, the action value, that is denoted as Q star of S comma A, that will take into all the environmental dynamics into account, which will be a kind of a dynamic programming approach, and that will be the most optimal uh, state value given equation can have, which is formulated by this term here. But in theory, it's a bit different. If we take a look at it, yeah, we can understand it. It's a bit of an intermediate representation between pure theory and uh, practical applications of the Bellman's equation in via the uh, code that we do. So if we take a look at this is the summation over S prime, that's the next state, is the T of S comma A comma S prime, which is the transition probability given the agent that choose the action A. And for example, in the above figure, this is 0.8 S2 to S0 given the A1 action that it chooses, S2 to A1 given the A1 it chooses. S2 to, sorry, S0 given the A1 action it chooses. That's this guy, 0.8. And the reward that it got was plus 40. This is the full parts that it got. Gamma is the discount factor. So this via this equation, then we give a max of this for all the E's. E are the actions. So in this value 8 iteration is estimated using the S at the kth iteration. Yeah, K is the number of iterations that we used over if we apply it, that's the number of iterations. How do we calculate it? Yes, alluded to earlier, it's an example for dynamic programming, which breaks down the complex problems into practical sub-problems, which can be tackled iteratively. Um, uh, this this factor, that's the value 8 iteration. There are multiple, how do I say, uh, in the current line of work, there are multiple uh, research avenues in trying to minimize the uh, cost and the time that's required to formulate this value iteration algorithms. That's the current research that was uh, interesting. Uh, And then this is also to be used for a optimal policy using the state action values, which is generally called the Q value, or the quality values. And it's the state action pairs, the S comma A, that's denoted by the Q star, and it's the sum of the discounted rewards the agent can expect on average after it reaches the state S and chooses the action A. And before it sees the outcome of this action, assuming it acts optimally after that action. So this is how the optimal Q value of a state action pair is defined as, how it is being formulated. Then how it works is, this is the Q k plus 1 S comma A, the summation over all the next states, with the transition probability is the reward functions plus the gamma of the max of the QK next state. So that's this. And we note that the phi star of S is trivial. When the agent is in state S, it should choose the action with the highest Q value for that state. So this is it. That's the optimal policy, which is given by the R max of K, Q star of S comma A. And then we define the MDP here, as we have seen. Yep, yeah. They have defined it here with how they have formulated these transition probabilities, the rewards, and the possible actions. Then they have given a simple NP using NumPy to give a full matrix of 3 by 3. We have bootstrapped this for negative of infinity for all the impossible actions, and for the each. So this is the environment dynamics that we have taken into account. And then we let our Q value iteration algorithm run with every state and possible action here. This has been copied. The Q values, that's a 3 by 3 matrix. All the possible actions are being iterated upon. So it's just a kind of a brute force summation and trying to come up with the rewards, the gamma, this equation that we looked at earlier. That's it. The resulting Q value looks like this. Since we have three, we have used a range of 3 here, 0, 1, 2. These are the and the possible actions that it could take. This is the formulation of the transition prop. I think so. We get it. We look at the code with respect to the discount factor. So the gamma here, it's taking as is taken as 0.9. So that's the hyperparameter that we choose. And then they have given a next 8 iteration to here in the code. I think so, with a discount factor of 0.95. Yeah. And this makes it goes to the fire instead of staying put. There was choose action A not and standard by choose action A not and stated. We'll have to take a look at it in detail. So let's stop here. We can take a look at this algorithm and how this works, and we can uh, start from temporal difference learning next time, because we are already 20 minutes over time. Let's take a look at how this works.
Yeah, that sounds good.
Hmm. So what they are doing here is firstly using a full matrix here, 3 plus 3. They haven't used TensorFlow here. This is a simple NumPy. The calculations here. This copy is being done to append this history with respect to at each iteration. What's the difference that it makes? Then this is the sum with respect to those transition probabilities. S in range 3, A in possible actions A, S, and the Q values S comma A and B dot sum. Transition probabilities S A S P multiplied by the rewards plus the gamma plus the max of the previous. This guy here. So this is this whole formulation that is being Q value equation algorithm that is being calculated here. Yep. So since this is dynamic programming approach, so the time required is very high because we aren't using any sort of approximations here. I'm just calculating the optimal, so it will be the highest. This is using the 0.9 discount, the gamma factor. This is it. Then they have done the same using the 0.95. Yep, it's same, the reward probabilities. What it will try to do is, if we prefer to go through the fire, since this policy has completely changed, then uh, agent values of the future is more with respect to those 0.95. If we take a look at it, and therefore it's kind of we can say a kind of a mm, uh, if I go back to your previous query with respect to those discount factors and how those future rewards are affected. This is a very good example of how agent now prefers to go through fire and chooses this action 8A2 via just 0.05, sorry, increment in the discount factor. And I think so they must have given it in the text too. 9. So, and the expected sum of the discount future rewards is 17 here in the case of 0.9. But in the 0.995, it goes to this goes to higher, and it makes sense because the more you value the future rewards, the more you are willing to put up with the pain now and for the promise of future bliss. That's how they are doing it. And this obviously has a very big impact in the future formulation, since this is just a simple uh, tabular representation of Q learning. But yeah, as we go deeper with uh, formnets or some sort of uh, how do I say it? Function approximations in place when we are trying to solve a complex environment, like paragraph for example. So this becomes very much in uh, this this will become a very much, how do you say it, uh, or simple if we take Atari or Mojoko in environments. This will is scale out and pan out to be a uh, very big factor in formulating our policies, the optimal, or we can also compare, uh, 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 how do I say it, those optimal policies with respect to those uh, um, policies that are calculated by using some sort of approximations and probabilities, probabilistic approaches. And when with respect to the equations that we apply, or the class of probabilistic equations that we apply to choose that next Q values. So that's for the next time, I hope. I have already been gone overtime by 25 minutes. So that's it for me now. Any queries, anything else? Please feel free to uh, ask in the chat as well.
Okay, so next time we'll start with temporal difference learning then.
Yep. We'll start with temporal difference learning and then go through the Q learning, and then we'll try to finish deep Q learning too, because that's in one go.
Yeah, remember we have scheduled 6 sessions, so this is only session 2. So you have, you have 4 more sessions to get through.
Yeah. But this becomes how do I say it, interesting, and if we go, I had opened this to give a basic, since I alluded to the fact that earlier that Bellman's equations are not defined as these, and this is just a kind of a from a practitioner's point of view. This is implementation of a Q value iteration and the value iteration for the Bellmans. But if we look at, I have even defined the page number. It's at I hope 63 or 64 in this book. So give a quick look at how those are formulated. Yeah. So those Bellman's optimality equations for the V star is like this. Yeah. That's the optimal condition based on how the correct mathematical formulation is and how it's derived. So this is the equation 3.19 and the equation 3.20. That is for the Q star, and this is for the V star. So that's just from the theory and how those backup diagrams for the V star and Q star work. Because if we look at those pure theory theorists, they will just disregard this. Yeah. So that was one. My
Okay, a good story for next time.
yeah.
Thank you so much for getting us this far in the reinforcement learning chapter.
Cool. Thank you.
And we'll see you on Sunday for
Yeah.
the next part.
Yep. Thanks, Mike.
Thank you. Thank
Good
you.
night, everyone, and good morning, Mike. Have a good day.
Yeah.
Okay.
Thank you.
Stay
Good
safe,
night.
everybody.